Airflow past a spinning cylinder is simulated in 2D under varying conditions using the Digital Dynamics Studio. This is a demonstration of the well-known Magnus Effect, which is a phenomenon that causes lift forces to be generated when a spinning object moves through a fluid. The motion of the spinning object, usually a cylinder or sphere, causes a low-pressure region to form on one side and a higher pressure region to form on the other. This, in turn, produces a lift force perpendicular to the fluid's direction, as seen here. The lift force induced by the Magnus Effect can be leveraged for many purposes, including many of the ball sports that we're all familiar with. Soccer, tennis, table tennis, cricket, golf, and baseball players can all use this effect if they are skillful enough. By spinning the ball, it will cause it to move in seemingly unnatural directions, which can deceive the opponent and result in a miss. However, this is a difficult skill to master and makes the game challenging. There are also many industrial uses of the Magnus Effect, including shipping. To save on energy, some unique designs called rotor ships, as shown here, have large cylinders attached that are mechanically spun. When there is a crosswind during travel in the open ocean, this wind induces a forward force similar to the force that a traditional sail would generate. This force then helps propel the ship forward and reduces its overall energy consumption. As can be seen in all of these examples, there are many uses for this flow-induced Magnus force, which we will explore in more detail here through simulation. In this first experiment, we are simulating airflow past a cylinder at a Reynolds number of 200. This number represents the ratio of inertial forces to viscous forces and is one of the main discriminators for incompressible flow applications like this. For this specific spinning cylinder application, another important parameter is alpha, which is the ratio of the cylinder's spinning surface velocity to the free stream wind velocity. As alpha increases, the generated lift forces also increase. However, the simulation results shown here are at alpha equal to 0, which, as you would expect, produces no net lift on the cylinder. Nevertheless, due to the well-known vortex shedding phenomenon, instantaneous lift forces are generated in a cycle from positive to negative, as shown here in the lift and drag graph. The lift forces are highlighted in red within this graph, but as can be seen over time, there is no net positive lift force. Before we increase the alpha parameter in this experiment, we want to first highlight the Digital Dynamics Studio's use of unstructured and adaptive grids, as shown here. This is an advanced technique that automatically ensures high fidelity and accuracy throughout the entire domain at all times. We can visualize either pressure, as shown here, velocity vectors, the vorticity field, and we can also add particle traces to help visualize the flow patterns even further. Now, we begin to increase the alpha values in the simulation. If you remember from before, the cylinder is spinning faster and faster as alpha values increase. The cylinder's lift and drag curves are shown here in the lower right. Alpha 0.0, Alpha 0.5, Alpha 1.0, Alpha 1.5, Alpha 2.0. The vortex shedding behind the cylinder has basically stopped at this point. Alpha 2.5, Alpha 3.0, Alpha 3.5, Alpha 4.0, Alpha 4.5, and finally Alpha 5.0. Shown here is a graph of the average lift and drag coefficients for each of the simulations in our experiment. As can be seen, the lift coefficient of the cylinder increases dramatically as the alpha spin velocity increases while the drag coefficient generally decreases. Our simulations and the resulting force coefficient graph match well with other results found in the literature. You might have noticed in the video that at an alpha of 4.5, there is some instability observed within the flow. In the alpha range of approximately 4.5 to 4.75, we observe a small zone of instability where some long-period vortex shedding takes place. This observed instability zone is also noted in the literature by other researchers. To visualize this phenomenon better, here we're showing a sped-up visualization of the Alpha 4.5 simulation. In this final experiment, we're simulating the same spinning cylinder at the same alpha values as before, but this time at a Reynolds number of 1000. The results are very similar as before, but the flow features are somewhat more refined with more detail. Alpha 0.0, Alpha 0.5, Alpha 1.0, Alpha 1.5, Alpha 2.0, Alpha 2.5. The vortex shedding has ceased at this value. Alpha 3.0, Alpha 3.5, Alpha 4.0, Alpha 4.5, and finally Alpha 5.0. The graph of the average lift and drag coefficients for each simulation at Reynolds number 1000 is shown here. As before, the lift dramatically increases with increased alpha value. Although different, this graph for Reynolds number 1000 is fairly similar to the results at Reynolds number 200 seen earlier. Also, as before, we observe an instability zone where vortex shedding happens for high alpha, but in this case, that instability happens around alpha 4.0, as seen here in a sped-up visualization. All of these simulations, visualizations, and analysis were carried out interactively within a web browser using the Digital Dynamics Studio from Digital Rocket Science.